In this section, we'll focus on the concept and the application of several different gas laws. A gas law is simply a relationship between two or more different variables as they affect a gas. In other words, a gas law explains how one aspect of a gas changes when we change another aspect. Some of these aspects of gas, or variables, include things like pressure. Pressure, of course, can have different units, but in gas laws we symbolize pressure as a capital P. Volume is another variable that can be changed, and volume, or the amount of space that a gas occupies, will be symbolized with a capital V. Another variable that's very important because it has a lot of effect on how a gas behaves is temperature. Temperature, which we'll symbolize with a capital T, can also have different units, although you'll notice that in most gas laws, your best bet is to work in units of Kelvin. In many cases, working in units of Celsius or temperature could give incorrect answers. Finally, the amount of gas that's present also has an effect on these variables. When we have to deal with amounts of gas, we'll typically do that in terms of moles of gas molecules, which we'll symbolize with a lowercase n. For each of the gas laws that we're about to cover, you'll notice that there are different ways to explain them. Some people prefer to explain gas laws as statements or explanations given in English about how a gas behaves. Other people prefer to use symbolic forms. And very commonly we see these different gas laws and their relationships written as mathematical equations. We'll do each for the different gas laws that we cover. The first gas law that we'll look at is what's called Boyles Law. Boyles Law describes the relationship between pressure of a gas and the volume of that gas. As is the case with several different gas laws, your own common experience usually gives you some hint as to the true nature of these different gas laws. Boyles Law relates pressure and volume, so let's think about this literally. Let's imagine that we have a container of gas. Inside this container, I'm going to put exactly 2 molecules of gas. We know that gas molecules have a fair amount of kinetic energy, meaning that they move around a lot. We also know that every time they collide with the sides of the container, they create pressure. So as these 2 gas molecules bounce around inside the container, each time they make contact with a wall, they create more pressure. For instance, if we focus on just one wall, you can sense how much pressure is occurring. Contact, 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 more pressure, more pressure, more pressure, more pressure. Each time those molecules collide, they create pressure. Boyles' law describes that pressure and how it relates to the volume of the container. So imagine taking this container away and replacing it with a container of twice the size. When I take the exact same molecules and set them in motion at the exact same speed or same temperature, look what happens to the pressure they create on the walls of the container. I'll go to the same wall and note how many collisions occur. Collision, contact, pressure, 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 and more collisions. It's just not as much as what happened when we watch the collisions in the smaller container. This truth is what's encompassed in Boyles' law. Boyles' law says that the more you increase the volume of your gas, the lower the pressure goes. And there's a number of different ways to state this. One of the most technical ways to state Boyles' law is to say that pressure and volume are inversely proportional. You probably already know that the word inverse means opposite or upside down. Proportional means goes along with or increases with. So to say that pressure and volume are inversely proportional simply means that as one thing goes up, the other thing goes down. That's one way to explain Boyles' law. You can also state this symbolically. Some people prefer to use the symbol for the word proportional, which looks, honestly, a little bit like a fish. We know that pressure and volume are inversely proportional, so to show that symbolically, we'd write that pressure is proportional to the inverse of volume. So that's another way that Boyles' law can be stated. However, it's not terribly useful because A, it's not in plain English, so it doesn't make sense to some people, and B, it doesn't do anything to help us solve this mathematically. This brings us to the mathematical expression of Boyles' law. The mathematical expression of Boyles' law is that if you take the pressure of any gas and you multiply it times the volume of that gas, you'll get K. K is used in science to represent a constant value, or in other words, a number that stays the same. Why does it stay the same? Well, think about what we just saw. When I doubled the volume of that container, I actually halved the pressure. I cut the number of collisions in half. By doubling V and cutting P in half, I keep K constant. For this reason, the other way you're likely to see Boyles' law stated is simply as the mathematical relationship P times V equals K. But either way, whether you say P times V equals K, or whether you say that pressure and volume are inversely proportional, you're talking about Boyles' law. Let's look at some other very simple gas laws. Similar to Boyles' law is a law called Gay-Lussac's law. Gay-Lussac's law describes the relationship between pressure and temperature. So now when we visualize a container of gas, instead of manipulating its volume, we'll manipulate its temperature to see what happens. This time I'll work with 4 molecules of gas, just to make it a little more interesting. As I set those molecules of gas in motion, every time they collide with the sides of the container, they create pressure. What will happen to the motion of these different gas molecules if I increase the temperature? In other words, if I make the temperature higher or make the container warmer. Well, a warmer container will have molecules moving at a faster speed. And the faster those molecules go, the more often they collide with the walls of the container. Because of this, Gay-Lussac's law tells us that as we increase temperature, the pressure inside a container will also increase. Unlike Boyles' law, we're not saying that as one thing goes up, the other goes down. Instead, we're saying as temperature goes up, the pressure also goes up. So Gay-Lussac's law is an example of a relationship between pressure and temperature which is directly proportional. In other words, as one increases, so does the other. If you increase the temperature of a gas, you increase the pressure of it. Mathematically, this means we wouldn't multiply pressure and temperature together to get a constant. We'd have to divide. So Gay-Lussac's law can also be expressed as pressure divided by temperature equals K. And in fact, sometimes you'll also see T over P, the inverse. But either way, the idea is that as one thing goes up, so does the other. Gay-Lussac's law says as pressure or temperature increases, so does the other. Let's look at our third and final named gas law that's really simple. This law is what's called Charles' law. And most of the time, Charles' law is stated as the relationship between volume and temperature. I think the easiest way to understand Charles' law is to picture something other than a container. The reason is the last 2 containers of gas we visualized had rigid walls. In other words, their volume had to stay the same. Charles' law works for situations where the size of the container can change. And a classic example of that is a balloon. If you fill a balloon with some molecules of gas, the temperature of that gas is going to affect the size of the balloon. You've seen this if you've ever taken a balloon outside on a cold day. If you have, you know exactly what happens when you lower the temperature on a gas. Provided that we're dealing with a flexible container, meaning something that doesn't have rigid size, that container will start to shrink or get smaller. The same is true if we go in the opposite direction. If we increase temperature, we also increase the volume, hopefully not so much that the balloon will burst. This is Charles' law, Based on this, would you say that Charles' law is a proportional relationship? One thing goes up and the other thing goes up? Or would you say that it's inversely proportional? As one thing goes up, the other thing goes down. What do you think? Well, Charles' law is an example of a proportional relationship. The higher the temperature of the balloon went, the bigger its volume got. Same thing with when we decreased temperature, we also decreased its volume. Charles' law is actually one of the principles that allows hot air balloons to fly. A hot air balloon has a large burner, usually supplied by something like propane gas, at the bottom of the balloon. This heats the air inside the balloon, causing the balloon to expand. It does not, however, put more molecules of gas into the balloon. Consequently, that larger space is less dense than the surrounding air because it has the same molecules, just in a bigger space. Charles' law says that volume and temperature are directly proportional. As one increases, so does the other. So like Gay-Lussac's law, it can be written as an expression or it can be written as a fraction that equals a constant. Typically something like V over T equals K. So far we've looked at Boyles, Gay-Lussac's, and Charles' law. And there's others out there. As long as you understand the basic relationships between pressure, volume, and temperature, you'll be able to use these gas laws just fine. What's interesting is that each one of these gas laws is not actually independent from each other. For instance, if I use one of the gas laws to interpret how a change in temperature might change pressure, I could also think about how that temperature would be changing volume. Let's look at a common example of gas laws at work that's working at your house right now. Modern refrigeration units, including your home refrigerator, use the gas laws to create a decrease in temperature. This is how both home refrigerators as well as large industrial refrigeration setups work. Initially, they start with a gas that's in a fairly small volume. That relatively small volume is usually accomplished by compressing the gas, many times by running it through very small, narrow pipes. That low volume, we already know, changes the pressure on the gas. The relationship between volume and pressure is Boyles' law, and Boyles' law tells us the smaller the volume of a gas, the larger the pressure. So when you run gas molecules through very narrow pipes, or you compress it into a very small place, you put it under high pressure. Finally, think about Gay-Lussac's law. How does having a high pressure affect temperature? Pause the video if you want to go back in your notes to check. Having a high pressure, according to Gay-Lussac's law, which says pressure and temperature are directly proportional, means that you'll also have a relatively high temperature. This is why the condensing unit on most modern refrigerators feels warm if you get near it. This is the area outside of the refrigerator. So how does refrigeration actually work? Well, in all cases, what happens is the pressure or the volume is released on that gas. Sometimes it's by releasing a piston. Other times it's by running that gas into larger pipes or expanding it. This means you have a higher volume. What goes along with having a higher volume is that that gas is now under much less pressure. And according to Gay-Lussac's law, when pressure decreases, so must temperature. So Gay-Lussac's law and Boyles' law together can actually explain a little bit of how modern refrigeration works. In addition to your refrigerator at home, which probably has a condenser and then expansion tubing, you probably have also experienced this if you've ever painted with spray paint or used one of those little cans of compressed air to clean off a computer keyboard. You'll notice that when you depress the button, allowing the gas to escape from the can gets colder. That's because you've released that gas into a higher volume and created lower pressure inside the container. These are simply gas laws at work. As we've just seen, these three gas laws allow us to state simple relationships between the variables of pressure, volume, and temperature. The advantage to these gas laws is their simplicity. The disadvantage is that each gas law only relates two variables. So what happens if you want to relate a change in pressure to both a change in volume and a change in temperature? Well, that's the tricky part about these three gas laws. They only relate two variables at a time. This is one of the reasons there's so many gas laws. We've just seen the examples of Boyles Law, the relationship between pressure and volume, Gay-Lussac's law, the relationship between pressure and temperature, and also Charles' law, the relationship between volume and temperature. In fact, your book even includes another law called Avogadro's law, which, as you might expect, relates the number of moles, in other words, a relationship to the amount of gas, to the volume of that gas. The downside here is that each one of these relationships is separate from each other. And in fact, the constants that you would use to solve them mathematically would have to be experimentally determined separately from each other. Each one of those values of K would be different. Because of this, most scientists prefer to use gas laws that encompass more than just two variables. What we'll see now is something that's called the ideal gas law. And we already said that an ideal gas is one that behaves according to the kinetic molecular theory of gases. The ideal gas law assumes that as long as a gas is behaving as an ideal gas, here's how the pressure, volume, and other variables will all be related. It's almost a deceptively simple law. The ideal gas law says that P times V is equal to N times R times T. You'll recognize some of these as variables. For instance, P stands for pressure, and V stands for volume. On the other side of the equation, we have three different variables. T is for temperature, which we already know has to be in Kelvin. N stands for the number of moles, in other words, the amount of gas present. This leaves us with one other symbol, which is a capital R. Capital R is not actually a variable. Instead, it's its own constant. The reason it's not represented by a K is that it's a very significant or very important constant in science. Generally, when a constant is assigned a letter unto itself, like R, it's saying that that must be an important constant that gets widespread use. This is what's called the ideal gas constant. It's a value that allows us to solve this equation for any one of the other variables: pressure, volume, number of moles, or temperature. The value of the ideal gas constant actually depends on what units you're using. It's very common to see it written like this. R, the ideal gas constant, is equal to 0.0821 with the following unit: liters times atmospheres in the numerator and Kelvin times mole in the denominator. While that may look like an overwhelming unit, it's really just a four-part unit. It's a little bit like miles per hour, just with a little bit more labeling. The advantage to having that strange-looking unit is that it tells us, in order to use this value for the ideal gas constant, our volume would have to be in liters. Our pressure would have to be in units of atmospheres. Our temperature would be in Kelvin, and finally we would also have the number of moles. There are other values for the ideal gas constant that have different units. For instance, sometimes you'll see R equal to 62.4. In this case, the units are liters times millimeters of mercury over Kelvin times mole. Notice the difference in the units between these two R values. The R value on top uses the pressure in atmospheres, while the R value on the bottom uses pressure in millimeters of mercury. You'll see how to use this in a minute. The ideal gas law is there to help you solve for any of the variables it contains: pressure, volume, number of moles, and temperature. You don't really need to ever solve for R because that's a constant that's always given. The way that you use it to solve for the variable is you just isolate the variable you want and you plug in the other ones you have. So this requires just some basic algebra. If you wanted, for instance, to solve for pressure, I locate pressure in the ideal gas law and then I would isolate pressure, meaning move all the other variables to one side of the equal sign. In this case, pressure is on the left side. It's also accompanied by volume, and I want to get volume off that side. So I'll divide both sides by volume to make it cancel. That cancels volume on the left side. And if I wanted to solve for pressure, my equation would be P equals N times R times T over V. That's the ideal gas law solved for pressure. If I would like to solve for something else, I can just, again, isolate my particular variable. So let's say you wanted to solve for moles. Thinking about our math, to solve for moles is really just isolating the variable N. So I want to move R and T to the other side. You can do this in one step or in two steps, but to get the R and the T off of the right side, I'm going to divide both sides by them. That will make them cancel. So I would see that N is equal to pressure times volume over the ideal gas constant times temperature. You can do this again for any variable that you want, and that's one of the reasons that the ideal gas law can be so useful. If you have the other variables, you can solve for the one that you want to know. Let's do an example problem. This is a classic ideal gas law calculation. What volume will a balloon have if we inflate it with 2 moles of oxygen gas at a temperature of 273 Kelvin and a pressure of 1 atmosphere? We're going to use the ideal gas law to solve for this, and it's really very simple. 2 basic steps here. First, solve for your unknown variable. So if you want, pause the video, see if you can solve the ideal gas law, or PV equals nRT, so that you can isolate the variable you're looking for. In this question, we're looking to find volume. So my ideal gas law is given as PV equals nRT, and I want to find volume. So I'm going to isolate volume by dividing both sides by P. That'll make P cancel, and the end result is I find that volume equals N times R times T over P. That's always my first step in solving the ideal gas law. Now I simply plug in the values to get my answer. My volume is equal to N times R times T over P. N is the number of moles, and the question tells me that I have 2 moles of oxygen. R is the ideal gas constant. Now I have to choose which value of R to use, and again, do this based on what you're given. In this question, my units given are moles, Kelvin, and atmospheres. So I want to look for the ideal gas constant that's as close to that as I can possibly get. When I look at my R values, one has liters times atmospheres over Kelvin times mole, while the other has liters times millimeters of mercury over Kelvin times mole. Because my question gives me atmospheres, I'm going to choose to work with the R value, 0.0821 liters times atmospheres over Kelvin times mole. Yes, I'm writing the entire constant in there, including the units, because as I mentioned before, if I have that in the problem, I'll be able to check and see if I did it correctly. That was my R value. Now I'm at T. My temperature is 273 Kelvin, and in ideal gas calculations, you will always need to be in Kelvin. So in this question, I was given Kelvin. If you were given Celsius, you would have to convert by adding 273. All right, so 273 Kelvin, that's my T, and now I'm going to plug in my value for P. 1 atmosphere is the question given in the, or is the number given in the question, so here's my setup. Before I solve this, I want to make sure everything actually cancels. So I'm going to look at my units, and I'm going to change to a different color so we can go through and see if everything cancels. First, I notice that atmospheres is on the bottom, and atmospheres is in the numerator of my R constants units. Then I notice that moles is in the numerator, but that's okay because moles is in the denominator of my R values constant. Now I look at Kelvin is in the numerator, and that's okay because again, it's in the denominator of the R values units. The only thing that hasn't canceled in the numerator is liters, and that's a good thing because the question asks for volume. So if I give my answer in liters, that should be appropriate. So my volume is 2 moles times 0.0821 times 273 Kelvin divided by 1. The answer I get is 44.8 liters. These really are just plug and chug calculations, but watch out because your units have to cancel. So if you're given temperatures and your temperature's in Celsius, you'll have to change it to Kelvin. If you're given a different unit of pressure, you may be able to use a different R constant, like 62.4 for millimeters of mercury, or you may have to change your units. And if you're given grams of oxygen, you'll have to do a gram to mole conversion in order to get to moles and plug into the ideal gas constant. The ideal gas law is great for solving for pressure, volume, temperature, or the number of moles. You simply isolate your variable and then it's all just plug and chug. The downside is the ideal gas law is difficult to use if you're looking at how one gas will change as you change pressure or change temperature. For instance, let's look at this example. If you exhale 4.5 liters of air at body temperature into a room that's 22 degrees Celsius, what will the new volume of the air be? Assume pressure didn't change during this process. If I try to use the ideal gas law for this calculation, everything's fine when you look at volume, which is 4.5 liters. But then you'll notice right away you have two different temperatures. Body temperature, which is the initial temperature of the gas, and 22 degrees Celsius, which is the room temperature or the final temperature of the gas. Based on that, it's going to be really difficult to use the ideal gas law because I only have one T, and I would have to choose which one to plug in. You could do this under certain circumstances, but you'd end up solving this equation at least twice. So generally we don't use the ideal gas law when it comes to variables that change, such as when you have more than one temperature, or more than one pressure, more than one volume, or any combination of those. Instead, we work with a specialized version of the ideal gas law that's called the combined gas law. The combined gas law simply isolates the variables that would change and sets them equal to each other. Because again, we know, based on Boyles Law, pressure times volume has to equal a constant, and based on Gay-Lussac's law, pressure divided by temperature would have to equal a constant. So from that, we get the combined gas law. The initial pressure times the initial volume divided by the initial temperature is equal to your final pressure times your final volume divided by your final temperature. These are no more difficult to solve than the ideal gas law because you simply isolate your variable and then you plug in your values. The downside is you have 6 different variables, P1, P2, V1, V2, T1, and T2. So it's easy to misread the question. For that reason, I really like to sit down and write out what my variables are before I start to plug anything in. So I'll look at this question and isolate the T1, the T2, and so on as I read it again, and that way I won't have to do that later on when I'm plugging in values. In this question it says assume the pressure doesn't change, and it doesn't give me any value for pressure. So I'm not going to worry about pressure, and you'll see why in a minute. It does tell me though that initially that volume of the gas is at 4.5 liters, and it's asking me to find what will the new volume be. That's V2. My initial temperature is 37 degrees Celsius, and my second temperature, or my final temperature, is 22 degrees Celsius. This is a good opportunity to look and see if I have any units that won't work. Any units are acceptable for the combined gas law as long as they cancel. So any units of pressure, any units of volume. The exception to that is temperature. And as you probably imagined, temperature has to be in Kelvin. So I'm going to add 273 to each of these Celsius temperatures so that I convert it to Kelvin. And I find out from that my first temperature is 310 Kelvin and my second temperature is 295 Kelvin. Now I'm ready to isolate my variables and plug in. My variable to isolate is V2, and if you want, you can pause the video and see if you can get V2 alone so that you can practice the algebra yourself. To isolate V2, I need to move the P2 and move the T2 to the other side. So I'm going to multiply by the inverse to make them cancel, and of course whatever I do to one side I have to do to the other. So P2 cancels, T2 cancels, and I'm left with V2 equals T2 times P1 times V1 over P2 times T1. The order and the grouping of the variables doesn't matter. The only thing that's crucially important is your numerators have to stay in the numerator and your denominators need to be in the denominator. At this point, you'll notice that pressure 1 is on top and pressure 2 is on the bottom. And in fact, you should never have two pressures on the top, or two volumes on the top, or two temperatures on the top, because they won't cancel. The fact that pressure stays the same is fine. It just means that I don't need to plug any numbers in for P1 and P2, because the pressure would cancel out. If I did have pressure values, I could just plug them in here. I'm left with T2 times V1 divided by T1, and now you can see why it's easy to have these information, that bracket, already ready to go. I can look here and see that my T2 is 295 Kelvin. I multiply that times my V1, which is 4.5 liters, and I divide it by my T1, which is 310 Kelvin. By having that information written out already, I'm less likely to plug a number into the wrong place. So I take 295 times 4.5 and I divide it by 310. And my answer with sig figs is that my V2 is 4.3 liters. So not surprisingly, when I exhale 4.5 liters into a cooler room, it condenses to about 4.3 liters. This is how you use the combined gas law.